Welcome back to the deep dive. Today, we're getting into one of the most critical parts of building any machine learning system, and that's model selection. I mean, if you've built 5 different classifiers, a logistic regression, an SVM, a few random forests, how do you actually rigorously decide which one is the best one for your problem? So for this deep dive, we've gathered sources that detail the essential methods for testing and, visually comparing them. The core idea seems to be that no single classifier is a silver bullet.
That's right. And our mission really is to give you the tools to make that choice reliably. And reliability is everything here. When you compare models, you have to be absolutely sure your performance estimates are solid. They need to predict how the model will do on data it has never ever seen before. But before we even get to the cool comparison tools, we have to start with the two big ways things can go wrong: overfitting and underfitting.
Okay, so let's unpack that. A model can fail in 2 completely opposite ways, and it seems like it usually traces back to the training data, right? To this thing called the bias-variance trade-off.
Exactly. Let's start with the first failure mode, underfitting. This is when your model is just, well, too simple for the job. Think of it like trying to fit a perfectly straight line to data that clearly has a curve in it. The model just isn't complex enough to capture the real pattern. When that happens, it suffers from what we call high bias.
High bias. Okay, so it's consistently wrong, but what does bias actually measure? What is it?
Bias measures the average error. I mean, how far off are the predictions from the real values in general? A good analogy is a ruler that's misprinted. Maybe the zero mark is 2 centimeters off. Every single time you use that ruler, your measurement is going to be wrong by about the same amount. That's systemic, consistent error. That's high bias. The model is just too dull to see what's really going on in the data.
Got it. It's a simple mistake, a structural one. So let's contrast that with the other extreme, which I think is a more common trap to fall into. Overfitting. This leads to high variance. Why do people get tempted by these overly complex models in the first place?
Oh, the temptation is always training accuracy. You build this incredibly complex model, like a super deep neural network or a massive decision tree, and it gets near perfect accuracy on your training data.
It looks amazing on paper.
It looks perfect, but it hasn't actually learned the underlying pattern. It's just memorized the training set, including all the noise and all the little quirks that don't mean anything. And that is high variance. Variance measures the consistency of a prediction for one specific example if you retrain the model over and over on different subsets of your data.
So a high variance model is jumpy, unstable.
Exactly. It's brittle. Its predictions for a single point will swing wildly from positive to negative depending on the exact data it was trained on.
Ah, so it's totally untrustworthy. It's great on the stuff it's already seen, but it falls apart with anything new.
Precisely. And that's the trade-off. You can't usually minimize both at the same time. If you make a model simpler, you reduce variance, but you probably increase bias. Make it more complex, you reduce bias, but increase variance.
So the whole game is finding that sweet spot, that Goldilocks zone, where it's just right.
That's the quest.
Okay, so let's say we have a model that seems to be in that zone. The next problem is that our standard testing method, just the single train test split, might still fool us. You could get lucky or unlucky with that one split.
That's a huge risk. Relying on one random split is, well, it's a gamble. If your test set happens to be really easy, you'll think your model is a genius.
And if it's unusually hard, you might throw away a perfectly good model.
Exactly. So we need a way to get a reliable estimate of performance that sort of averages out all that randomness.
And this is where we get into the really rigorous stuff. This brings us to k-fold cross-validation. This is the technique that gives us that stable, reliable number. Can you just, walk us through how that actually works?
Sure. So instead of just one test set, you take your entire data set and you split it into, say, 10 equal chunks or folds. That's your K. So K equals 10. Then you train your model 10 separate times. Each time you use 9 of the folds for training and the one leftover fold for testing.
And you rotate which fold is the test set each time?
You got it. So by the end, every single data point has been in the test set exactly once. You get 10 different performance scores and you just average them. That average score is a far, far more reliable estimate of how your model will perform out in the wild.
Okay, that makes total sense. It smooths out the bumps. But we can still do better, right? Especially when the data isn't perfect. Let's talk about the enhancement, stratified k-fold cross-validation.
Yes, and this isn't just a nice to have. For a lot of real-world problems, it's an absolute necessity. It's critical when your classes are imbalanced.
Imbalance, meaning one category shows up way more often than the other.
Right. Imagine a data set for fraud detection. Maybe 95% of transactions are normal and only 5% are fraudulent. That's a classic imbalance problem.
And what happens if you use regular k-fold on that?
Well, there's a real chance that just by random luck, one of your test folds might end up with 0 examples of the rare class,
Yeah.
0 fraud examples. So when you test your model on that fold, it gets a perfect score for detecting fraud because there wasn't any to detect. Your metrics for that fold are completely misleading.
Wow, okay, that's a huge blind spot.
It is. Stratified K-fold fixes this. It makes sure that each and every fold has the exact same ratio of classes as the original dataset. If the whole thing is 955, every single fold will be 955.
So every test is a fair test.
A much fairer test. It gives you way better estimates of your bias and variance.
And you see this in really high-stakes applications. The sources point to things like the breast cancer Wisconsin dataset. You can't afford to have a misleading performance score when you're trying to detect cancer.
Absolutely not. The cost of missing a true positive is just too high. The rigor has to be there.
Okay, so we've used stratified cross-validation. We have these stable, reliable performance numbers for a few different models. Now, how do we actually compare them? Go beyond just a single number like accuracy.
This is where we need a visual tool. And the classic one, used everywhere from medicine to machine learning, is the receiver operating characteristic graph, the ROC curve.
The ROC curve.
It's an amazing tool. It's designed to show you the relationship between two competing metrics as you change your model's decision threshold. Specifically, it plots the true positive rate. So how many of the actual positives you correctly identified against the false positive rate? How many false alarms you raised?
But before we get into reading the graph, there's a big warning label on it, right? When is the ROC curve maybe not the best tool?
That's a great point. ROC curves are fantastic when your dataset is more or less balanced. But if it's severely imbalanced, like that fraud example where it's 99 to 1, the ROC curve can be visually deceptive.
Why is that?
Because with so many true negatives, your false positive rate stays tiny, even if your model makes a lot of mistakes. The curve looks great, pushed up near the top left, but it's hiding the real story.
So for those really skewed cases, what's the alternative?
In those scenarios, you should turn to the precision recall curve. It focuses much more intensely on the performance on that rare positive class, so it gives you a much more honest picture.
That's a critical distinction. Okay, so assuming our data is balanced enough, let's look at the ROC graph. What tells us if a model is good or bad?
The first thing you look for is the diagonal line, from the bottom left to the top right. That line is random guessing.
Flipping a coin.
Exactly. Any model whose curve falls below that diagonal is literally worse than random. You throw it out immediately. A good model has to have a curve that bows up and to the left.
And the more it bows, the better.
The more the better. The perfect theoretical classifier would be a point right in the top left corner. That means you have a true positive rate of 1 pi-er. You caught every single positive and a false positive rate of 0. No false alarms.
The dream scenario.
The dream. And every real model is trying to get as close to that corner as possible.
Which leads us to the single metric that summarizes that whole curve. The area under the curve, or AUC.
Right. The AUC collapses that entire curve down to a single number, from 0.5 for random chance up to 1.0 for that perfect classifier. It tells you, on average, across all possible thresholds, how well your model can distinguish between the two classes.
So if you're comparing Model A and Model B, the one with the higher AUC is generally better.
Statistically, yes. It's the superior classifier overall.
And you just said something really important there, across all possible thresholds. That's the real strategic part of this, isn't it? The ROC curve doesn't just help us pick a model, it helps us pick the threshold, the cutoff point for making a decision.
This is where the whole thing becomes about business strategy, not just statistics. The best model might not be the one with the highest AUC if its operational trade-offs aren't right for your problem.
Explain that. Let's look at those conceptual points on the curve. Say, a point close to the bottom left.
Okay, let's call that point A. You're at a point with a very low false positive rate, but also a lower true positive rate. This is for situations where false alarms are incredibly costly. Think about a bank flagging a transaction as fraud. Every false positive means a customer's card gets blocked, they get angry, you have customer service costs. It's a huge pain.
So in that case, false positives are more costly than maybe missing a few actual fraudulent transactions.
Exactly. You intentionally pick a high threshold at point A to minimize those false alarms, even if it means you're a little less sensitive.
Okay, now let's go to the other side of the curve, closer to the top right.
Let's call that point C. This is the opposite scenario. This is where a false negative missing a true positive is a catastrophe.
Like our cancer diagnosis example, or maybe an airport security scanner.
Perfect examples. Here, you absolutely cannot afford to miss a real threat. So you choose a threshold that maximizes your true positive rate, even if it means you get a lot more false alarms that need to be checked out later. Safety is paramount.
So the threshold is purely a strategic choice based on risk. And I guess point B, somewhere in the middle, is the compromise.
Point B is usually that balanced sweet spot. The default threshold often lands you there. But the key takeaway for you, the listener, is that model selection isn't just about finding the highest AUC. That's statistical excellence.
You're aiming for operational excellence.
You are. You might have one model with an AUC of 0.91 and another with 0.89. The first one is statistically better. But if the second model gives you an operating point that hits 99% of true positives at a cost you can live with, and the better model can't, you pick the second one.
The curve itself, the trade-offs it shows you, is more important than the single AUC number summarizing it.
It is absolutely the most valuable piece of information for making a real-world decision.
That really ties it all together. You have the whole framework now to move way past just guessing.
We really covered the whole arc. We started with the fundamental problems, navigating that bias-variance trade-off. And we got into the rigorous testing you need stratified k-fold cross-validation to get reliable numbers. And finally, we landed on the strategic tool, the ROC curve and the AUC, for comparing models and, more importantly, for choosing a deployment strategy based on cost and risk.
So you now have the tools to not just build a classifier, but to test it, compare it, and deploy it in a way that truly solves your specific problem.
Right. And just to leave you with one final thought, we know the ROC curve helps you pick a threshold based on minimizing real-world cost. The AUC summarizes that performance across all thresholds. But what if you're in a situation where the costs of false positives and false negatives are dynamic? They change from day to day. If that's your world, how might relying only on that single average AUC score actually mislead your strategic decisions? Think about what you lose when you boil that entire strategic landscape down to just one number.